Okay, so for today we'll be going through the material, all right, on the instructions and architecture, the encoding of instructions, and see how all of that comes together. Okay, so before that, we will have some other activities first, just to recap some of the MIPS assembly language concepts. All right. So let's just before we'll do a poll everywhere sort of competition. Okay, so let me get it out first. Just give me a minute. Let me just check the settings of the. Okay, so can you all start to log into the poll? Okay, so you'll be able to see a snippet of a code. All right, and we're going to sort of review it line by line first. Okay, and then we will see how everything comes together. Okay. Okay, so we'll do line by line, and then we will see how it sort of comes together in the end. Okay, so this is basically a code that can sort of run on Qtspim. Okay, so I hope you have tried it. So it sort of helps you with your assembly language. So you can only answer once. Okay, you can't change your answer after that, and you have 60 seconds for each question. Okay, so time is up. All right, so the correct answer is FFAA1122. All right, so let me again make sure that we understand what is happening. Okay, so this is basically the code that we have. All right, so what is happening is in the very first line over here. So LA is load address, so it's a pseudo instruction. Okay, the pseudo instruction that loads the address of this label into S1. All right, so S1 is now basically pointing to where value is. So value is basically a label for or sort of the name of this sort of array of elements. All right, so the very first element is FFAA 1122. The next element is 11112222 and 55556666. All right. So in this case, each element here or each sort of memory block here is 4 bytes, correct? So because it's defined as a word, so everything here is occupying a 4 byte space. So by default, the value points to the first element. If I want to point to the next element, then I'll say +4 and so on. All right. So when I load address S1 value, so register S1 is going to have the address of where it is. So this address is, if I'm not wrong, QT stream is, let me see, is kind of the exact address, but it's 0100100 or something like that. Okay, but never mind. Okay, what is the actual address doesn't matter, but we know that when I load this address inside, okay, so let's say that's the address, 0x01001000. Then subsequently, when I execute the second line, I'm taking to wherever S1 is pointing to. So where is S1 pointing to? Okay, S1 is pointing to this address, and I take a word from there. Okay, so the offset is 0, so there is no offset. So whichever value is loaded in S1 is the address, and I take the word value, that means the full 4 bytes, and put it into T1 register. So this information goes into register T1. Okay, 0xFFAA1122. Okay, so that is the first thing that is happening here. All right. So let's continue with this. Okay, so if anything you're not sure, you can just ask. Okay, so after line 4 is executed, what is the value in T1? So we know that line 2 loads the data, then I do something in line 3 and I do something in line 4. So after line 4 is executed, what is the value in T1? Think about it. Okay, so time is up. So let's see what is the answer. Okay, so most of you got it right. So the answer is 0000FFAA. Okay, so let's just be sure that everybody has the correct understanding. So in line 3, what happens? You are adding T1 with 0 put into T2. So effectively, I'm making a copy of T1 and putting it into T2. So add with 0 and put somewhere else is just a copy function. Okay, so 0xFFAA1122. Okay, so T1 and T2 now have the same data. And then in line 4, what am I doing? I am shifting right T1 by 16. So when I shift right T1 by 16, the lower 16 will disappear. Okay, so basically what I have is 0xFFAA1122. When I shift to the right by 16 bits, then this lower 16 bits will disappear, and what will shift in is 0 will shift in to replace the 16 bits. Okay, so I will then have 0000, and this will come here. So FFAA. Okay, so that is what is happening when I finish line 4. Okay. Okay, then when I complete everything, what happens? So in line 7, I finish everything. So you must look at line 5, line 6, and line 7. Okay, so time is up. Let's see. Okay, so the correct answer is 2211 AAFF. So let me just bring it up here. So what is happening? In line 5, we do an AND of T2. So what is in T2? FFAA1122, and I do an AND with 0x FFFF. That means it is 0x0000 FFFF, and I do an AND operation. So I do an AND with 0, it becomes 0. And I do with an F, it retains, so it becomes 1122. Okay, and then what do? I shift left T2 by 16. So when I shift left by 16, okay, this leftmost 16 will disappear and this will come here. All right, so what I will have is 0x1122 and I'll have 0000. Okay, so that is in my T2 register. So this is your T2. And in the last step, I do all of T1 with T2 put into T1. So what is in my T1 register? T1 register is 0x0000 FFAA. Okay, so when I do a OR with 0, I retain the original value. So I will get 0x1122 FFAA. Okay, so basically what does this code do? It takes the original 32-bit data and swaps the upper 16-bit with the lower 16-bit. Okay, so the lower 16-bit will become the upper 16-bit and vice versa. Okay, so that is what this small code here is doing for us. Okay, so and also of course this you could probably do it in other ways as well, but as long as you understand what each of these instructions are doing, okay, then I think that is important. Correct. So you are able to relate to the memory instructions, the logical instruction, the shift instructions, and so on. Okay, so that is the, I think there's one more question. Okay, so this is one more question, not related to the code, but just to give you, to make sure I understand all the instructions clearly. What instruction will load a value of this into register S2? Okay, so time's up. Let's see what's the correct answer. All right. All right, so load immediate, okay, is the correct instruction. Okay, so just okay, so the first two, of course, you can't write that because your immediate value is only 16-bit. Okay, so load immediate, you can use 32-bit data. All right, but of course, you don't have two registers, you have one register. Okay, so that is the end of the first quiz. I have one more quiz, which is more in line with what we are doing today. Okay, so load immediate is basically, okay, so if you look back at your MIPS instruction set, let me see. So load immediate is considered a pseudo instruction. Okay, it's a pseudo instruction, which means when you write load immediate, it actually compiles into two separate instructions, which is the load upper immediate and all with the lower 16-bit. Okay, so I think in your lecture slides, you have seen how that works, correct? That means when you want to load a 32-bit value, you have to load it in two halves, correct? One is the load upper immediate, and then you all with the lower 16 bits. All right, this load immediate is just a pseudo instruction that when you compile, actually translates into those two instructions. Okay, so that is why it allows a 32-bit immediate data. Okay, so let's try another one. Okay, so these are questions, I would say, more related to what we're going to be covering for the quiz review. Okay, so which of the following requires the processor to perform an addition operation? Okay, so time's up. Let's see what are the answers. Okay, so everybody got the first and last, but everybody missed out on load word and store word. Okay, load word and store word, the processor is still performing an addition operation, all right, because you have the base register S0 add with the offset. Same thing for store word, base register add with the offset. It is an implied addition, correct? So we don't explicitly say add, but the processor does perform an addition operation. Only thing, it is an implied sort of operation. Okay, so always remember, load word and store word do have add operations. Okay, so all this you must be clear, because when we are looking at the processor architecture and we see how it is designed, all these things will sort of make sense. Correct? Why we write the instruction in a certain way, why certain registers are involved in a certain way, and it all come back like one full circle when you see how the processor is designed. Okay, so just remember, load word and store word also perform an addition operation. Okay, this should be quite easy. All MIPS instructions have a 6-bit opcode. Okay, so time's up. Okay, so true. All right, so it's very obvious. So all your R type, I type, J type all have a 6-bit opcode. Okay, that's good. Okay, so the load word instruction and add instruction utilize the 32 bits of an instruction in a similar manner. Okay, so the answer is true. Okay, so why do I say it's true? Because for both load word and add the instruction is the same. You have an opcode, you have RS, RT, and immediate. All right, and what you're doing is the same. You're taking your RS plus your immediate, and you're putting it, or you're using it for some operation, correct? But in terms of the actual 32-bit instruction, it is the same format. You have opcode, RS, RT, and immediate. So the way the 32 bits of instructions are utilized is exactly the same. Okay, load word and add would be different because add is an R type, whereas add I is a immediate. So load word and store word are also considered as immediate or I type instructions. Okay, the only thing is the way the outcome is used is different. In add I, the outcome of the addition is the final answer. In the load word, the outcome of the addition is the address that you're pointing to, and then the contents of the memory location are the final answer. Okay, different instructions can have the same opcode. Okay, this one also should be quite obvious. Okay, so the answer is true, correct? And this is what you see for the R-type instructions, correct? When you look at the R-type instructions, okay, if you look back at your instruction set, you see that for many of them, the opcode is 0, okay? But then the function field is the one that differentiates. Okay, so for all your R-type instructions, the opcode is still 0, the same. Okay, but your R-type, your function field is the one that differentiates, okay, which operation you're carrying out. Okay, so that brings us to the end of this. Okay, so I have one more thing that I want to do before we start the quiz. All right, so I hope you have some writing material. So I have a code challenge for you all to try. Okay, so I'm going to give you some time to try, and then I will sort of go through with you. All right, so the code challenge is this. Okay, so if given any random value in register S0, write a program to check if byte 0 and byte 3 are the same. So I give an example. So let's say in S0, this is the data 1, 1, 2, 3, 4, 5, 1, 1. So byte 0 is this, the least significant byte. Okay, and byte 3 is this, the most significant byte. So if they are both the same, then I put a 1 into register T0. If they are different, that is byte 3 and byte 0 are different, then I put a 0 into register T0. Okay, so I hope you give it a shot. Don't just eye power and wait for the answer. All right, just take out a pen and paper or something and just try to write it out or type it out or something. Okay, so many times only when we start writing the code we realize how much we don't know. All right, so it's good to always try it out. Okay, so I'll give you a few minutes, okay, to attempt it first, and then I will sort of go through just one possible solution, okay, and then we'll run it through the Qt spin just to check that it is working. Okay, so I'll just give you a few minutes to attempt it first, and then I will come back to discuss it. Okay, so I hope that you have given it a shot. Okay, so since I'm going to run it in the QT stream in a while, put it properly. So the dot text is basically to put it in the code segment. All right. Okay, so what I'm going to do is I'm going to first load S0 with values on 1, 2, 3, 4, 5, 1, 1. All right, then later we'll just change this value. Okay. Because I'm just going to sort of run through the idea. You may have different implementation, as long as it works, is fine. All right. Okay, so what I'm going to do is I'm going to put a value of 0 into T0 first. Okay, so I'm going to add 0 with 0 put into T0. Okay, so why am I doing this is so that I have a default value for the false case. All right, so I don't need to do unnecessary branches. All right, so I only need to do a branch sort of if it's true. Okay, or false. So yeah, either way. Okay, so it depends on how you want to look at it. So I'm going to just keep a default value of 0. All right, in T0 first. So that would be the false case. And then what I want to do is I want to extract out the byte 0 and byte 3. All right. So the first thing I can do is I can say AND I, okay, S2 S0 with 0x 00FF. Okay, so this is of course a 16-bit value, and if you look back, okay, if you remember last week we looked at the instruction set and we said that there's another 32-bit pattern in front. All right, so what will this do? This will make sure that the except for the last 8 bits, everything else is 0. So I'm basically extracting out this last least significant byte, okay, from S0, and I'm putting it into S2. All right, so that is what this line is doing. I'm extracting out the least significant byte and putting it into S2. All right, then what I want to do is I want to extract out the okay, I'll put this into S1 first. Okay, then I want to extract out the upper 8 bits and put somewhere else. Correct. So for the upper 8 bits, how can you do it? Again, you may have different ideas. So what I'm going to do is I'm going to do a shift operation. Okay, S2, S0, and 24. Okay, so what does this do? It will take S0, which is this value, and shift it to the right by 24. When I shift it to the right by 24, the lower 3 bytes will disappear. Correct, will be shifted out. All right, when that happens, the most significant byte will now be in the last position here. It will be the last position. All right, so basically what is happening is, okay, so when I do an AND operation, okay, then I'm taking the data, which is 0x 1 1 2 3 4 5 1 1, and I'm only keeping this data. So what is left in register S1 is 0x0000000011. Okay, and then what I'm doing next is I'm doing a shift right logical of S0 by 24 bits and putting it into S2. So what does that do? This upper 24 bits, that means 0x11234511. So this this lower 24 bits will be shifted out. Okay, and this bit will be shifted here. Okay, so what I will get is 0x00000011. That will be in my S2 register. So you can see that now for both my S1 and S2 registers, I have, this is your byte 0 and this is my byte 3. Okay, and then I can go ahead to do a comparison. So in this case, if it is not equal, S1 with S2 is not equal, then I go to next. I don't need to do anything because T0 is already set as 0. But if it's equal, then I need to update T0. So I can do add I T0 with 1. Okay, so I will only update T0 to 1 if they are equal. If it's not equal, I will branch to next, and it's fine because I have already set the default value to 0. Okay, so let's just step through this intuitive PIM. Okay, so let me step through this. Okay, so this is the main. Okay, so as you can see, the first line here, okay, you can see here the first line here is load immediate with 32-bit value. Okay, but what the compiler does is it actually breaks it up into two different instructions: the load upper immediate and the OR with the lower 16 bits. All right, so that is showing you how the pseudo instruction is actually broken up into two separate instructions. Okay, then the next step is, okay, come, let me move it back here. All right, so okay, so you can see the S0 has this value 11234511, and then I'm going to add 0 with 0, put into my T0 register. Okay, so T0 has a value of 0, and then I AND my T0 with FF and put into T1. So you can see that, sorry, put into S1. Okay, so S0 AND with 0xFF and put into S1. So S1 has the lower byte, and then I do the shift, and then S2 has the upper byte. So they are both the same. So I update T0 with a value of 1. Okay, so you can see it works. Okay, just to confirm, you can just change this to 2 over here. So I change the upper byte and lower byte. Okay, so now when I run through, okay, so you can see that now this is the new value 11234522. Okay, so I go through the same steps. So you can see now that S1 is 22, the byte 0, and S2 is 11, the byte 3. And now I will branch if not equal. Correct. So I will not update T0. Okay, so that is just a short example. Okay, hopefully that gives you some practice as well. Okay, so again, as long as you can get some practice with QT-SPIM, please try and do it. Okay, so that you get better at it. Okay, I know most of the tutorial we analyze code. Okay, but it's also good to write your own code. Okay, so you know how to think through the logic. Okay, and plan out how to use your registers. Okay, so if there are any no questions on this, I think we can actually proceed on to the yeah, I actually have a variation of this, but now let's go through the quiz discussion first, and looking at the time, then we will decide whether to come back. Okay, so let's go through the quiz questions. Okay, so for the quiz questions, you're asked to first encode this. Okay, so let's go through it step by step. So for add I instructions, add I register 9, register 10, and negative 32. Okay, so we know that this is the immediate value, and this is your RS, and this is your RT. Okay, And for add I, the opcode, you can always look back here. All right, so look back at your instruction set. So you can see that the opcode here is 8. Okay, so that is 0x8. Okay, so once you have all of this information, the rest is, I think, quite standard. You just put everything in together. So you have your opcode. So this is a 6-bit opcode, 5-bit RS, 5-bit RT, and 16 bits of your immediate. Okay, so let's put in the values. So opcode is 0x8, so 0, 0, 0, 1, 0, 0. Okay, so this is RS, this is opcode, this is RS, this is RT. So this is 10, so that is 1, 0, 1, 0, 0. And this is 9, so 1, 0, 0, 1, 0. And negative 32. So, okay, by now you know how to do all this conversion. All right, so you can just key in 32. Okay, negate, and you get that. All right, so this is of course 64-bit. Okay, we're just taking 16 bits. So basically what you have is 0, 0, 0, 0, 1, 1, 1, 0, and the rest are all ones. Okay, then once you're done with that, it's just grouping it into hexadecimal. 1, 2, 3, 4, 1, 2, 3. Yeah, so this will give me 2, 1, 4, 9, F, F, E, 0. Okay, so I think that should be doable. All right, so it's just a matter of mapping the instruction to the various parts of the opcode, RS, RT, and so on. Okay, so let's go on to question 2. In the following code, encode the first BEQ instruction. Okay, so the first BEQ instruction, it says that BEQ S0, S1 to exit. Okay, so basically we know that when I fetch this instruction, my program counter is pointing here, but the moment I fetch and execute this instruction, my program counter increments to this location here. Okay, to PC plus 4. So from PC plus 4, exit is over here. So I need to see how many lines am I away. So this is 1, 2, 3, 4. So total of 4 lines away. A total of 4 lines. So it's always the number of lines of code I am away from PC plus 4. Okay. So with that, we can actually do the encoding. So BEQ. Okay. So S0, S1, and exit. Okay, so S0 is register 16, this is 17, and this is 4. Okay, BEQ, again, you can look at the instruction set is 4. Okay, the rest is just putting it inside the format. So opcode. Okay, RS, RT, and immediate. Okay, so this will be 4, 0, 0. So RS is S0. Okay, so this is 16. This 16 is 1. This is 0, 0, 1, 0, and the rest are all zeros. Okay, so The rest is standard. So this will be 0004. That part we know. 1, 2, 3, 4. This will be 1, 2, 1, 1. Okay, so I think the key takeaway here is this number here. Okay, how to make sure you get the correct line offset. Okay, so of course, if you remember, we said that each line is, or each instruction is 32 bits. Correct. So in terms of number of bytes that I need to offset by is actually a multiple. I need to multiply by 4. Correct, and that is actually done by the hardware. Okay, so when we are looking at the architecture, you will see how this number here, this number of lines here, actually translates into offset in terms of number of bytes that you will adjust the PC by. Okay, so that one probably in the coming lecture you will see. Okay, when you're doing the architecture. We convert the MIPS machine code into assembly language. Okay, so let's do this. So this is 8D. Okay, so if you just write out everything, so you're 1 0 0 0 1 1 0 1 1 0 0 0 1. No. One. Then FF 1 2 3 4 1 2 3 4. Okay. So first thing is opcode 1 2 3 4 5 6. Alright, so whenever you're going in the reverse order, let me given the machine code and you're supposed to decode, always look at the opcode first. Okay, because when you look at the opcode, you will straight away know how to interpret the data. So when you look at this, this is 0x23, which is actually a load word instruction. Okay, so once you know it is a load word instruction, you can straight away do the rest. That means you know that this here is the immediate value. Okay, and this is 1 2 3 4 5. So this is your RS and this is your RT. Okay, so this is 12 and this is 11. All right, now the thing here is the immediate. So as we know, the immediate is always 2's complement 16-bit number, which means that whenever the most significant bit is a 1, I cannot take the value as it is. I need to 2's complement it to know the actual value. So if I do a 2's complement of this, all right, which is flip plus 1, I will get 227. And because of the most significant being a 1, I must put a negative in front. Okay, so once you know that, then the rest is just putting it together. So you know load word. Okay, my source register is register 12. Okay, and I'm putting an offset of negative 227, and the destination register is register 11. Okay, so that is your question 3. Okay, question 4, convert the MIPS machine code. Okay, so again, the same thing, we are going to start 0 0 0 0 0 0 0 1 0 0 1 0. Okay, so the first thing is opcode 1 2 3 4 5 6. Okay, so in this case, the opcode is 0. Okay, which means that it is R-type instruction. So we need to look at the function field. So 1 2 3 4 5 6. Okay, so the function field here is 2. All right, so if you look back at your instruction set, okay, opcode slash function. Okay, so this column here is opcode slash function. Okay, so I need to look at which opcode is which function field is 2. So the function field that is 2 is this. Okay, opcode is 2 and function field, so opcode is 0 and function field is 2. Okay, which is what we have here. So we know it's a shift right logical. Okay, so for shift right and shift left, okay, we know that the shift amount is specified here in the 5 bits over here. So 1, 2, 3, 4, 5. So this is value 7. So we are shifting it by a value of 7. All right, and we are using RT and RD. So this is 1, 2, 3, 4, 5. This is your RD 1, 2, 3, 4, 5. This is your RT. So I'm shifting RT, which is register 18, register 18 by 7, and putting it into register 17. Okay, so it's equivalent to S1, S2, 7. Okay, so that is your question 4 here. Okay, question 5. The program counter. Okay, so the program counter stores the address of the next instruction to be executed. All right. Okay, so it always points to the next instruction. The moment I fetch the instruction, it automatically increments by 4. Okay, but of course, since the okay, so actually the next statement does that. Gets incremented by 4 unless there is a control flow. Okay, so a control flow is a branch or a jump or something like that. Okay, so when that happens, all right, what we will do in the hardware is we will change the or update the value to the correct value. Okay, depending on whether I'm taking the branch, all right, or with the jump instruction or so on. Okay, the size of the PC is 32 bits. Okay, which is true. Okay, the programmer updates the value of PC using add-I instruction every time, which is not true. Okay, this updating is done automatically through the hardware. Okay, so you will see that shortly. All right, or maybe you already covered it in the videos. I'm not very sure. Okay, but basically the PC or many of the blocks are controlled through hardware. Okay, so the PC is one of them, where the addition of 4 is done automatically through the hardware. Okay, which we will see. Okay, choose the true statements. R format instructions only have registers as operands, except the shift instructions. Okay, which is true. Okay, so for R format, you only deal with the data in the registers. Okay, the only exception to that is the shift. Okay, only for the shift amount is specified as part of the instruction. Okay, and not in the register. Okay, I format instruction has at most 2 registers and 1 immediate operand, which is also true. All right, so your add I or load word, all of them at the same format. That means you have 2 registers and 1 immediate. Okay, the J format instruction uses label that is stored in one of the register. No, that is not true. Okay, all the 3 instruction formats are 32-bit long. Okay, which is true. Okay, R, I, and J all are 32 bits long. Okay, the label in branch instruction refers to the number of instructions where the label, whereas the label in jump instruction refers to the partial target address. Okay, so this is true. Okay, so again, what we're saying here is when you talk about branch, it is always based on the number of instructions away from the current PC plus 4. Okay, like what we saw just now. Again, when we did this calculation here. Okay, is the number of lines away from the current PC plus 4. All right, but whereas when I use a jump instruction, okay, I'm actually providing a partial address. Okay, I'm providing a partial address, a 26-bit address, and then from a 26-bit address. Okay, so if you remember from your notes, what happens is in your jump instruction, you have your 6 bits of code and you have a 26 bits. All right, so what does the processor do? This 26 bits it adds another 2 zeros. Correct? Why 2 zeros? To make it 28. And why is it always 2 zeros? Because when you jump, you're always jumping to a word aligned address, because all the instructions are word aligned. Okay, so you always branch, or you always jump, or you branch also to a word aligned address. All right, because instructions are all word aligned. So the only thing that is missing is, so now you have 28. The only thing that is missing is your current 4 bits, upper 4 bits. So that is taken from the current PC plus 4. Okay, so plus this 4 will give me my 32. So in the jump instruction, we are providing a part of the target address. All right. For a 16-bit, okay, so 16-bit fixed length instruction. Okay, there are 2 types, type A and type B. Okay, so they ask us to look at what is the maximum number of instructions that can be formed. Okay, so we're trying to maximize this instruction set architecture design that we have. Okay, so what we have is in A, we have, okay, so we have 4, 4, 4. All right, and then we have another 4 here, which we can set aside for the opcode. Okay, because 4 bits each for the operand. All right, whereas for B, we have 2 4-bit operands. Okay, and you have another 8-bit here. Okay, that is for the, that we can set aside for the opcode. Okay, so in order for me to maximize, okay, so to maximize, what I can look at is how I can maximize B and minimize A. Okay, since B has more number of bits, it makes sense to maximize B. All right, because I have a lot more combinations. Okay, so to minimize A means the minimum I can have is just 1 opcode. Okay, so let's for example, we say we set aside 0000 as reserved for A. Okay, so for B, what do we have? So for B is 8 bits. Okay, but since we know that the upper 4 bits of 0000 are reserved for A, we start with the next one, which is 0001 all the way to 1111. Okay, so for B, we know that for each upper 4 bit, which is a value 0001, for example, I have another 4 bits here, and this 4 bits is basically going from 0000 to 1111, which is 2 to the power of 4. Okay, so that means that the total number of instructions that I can have, okay, in this entire section here is 2 to the power of 4 minus 1, and for each of this I have another 2 to the power of 4 each. Okay, which will give me 240. And for A, I reserve 1. For B, I have 240. Okay, so that is the sort of max or maximum number of instructions that I can get. Okay, with this. Okay, to minimize this. Okay, to minimize this, I can think of minimizing B and maximizing A. Okay, so if I say minimum, I say minimize B and maximize A. Okay, so if I say minimize B, okay, or maximize A. So for maximize A, you can say that I have 0000 all the way to 1111. Okay, but since I need to set aside 1 for B, let's say I reserve this Okay, so what is left is from 0, 0, 0, 1. So it's 2 to the power of 4 minus 1, which is 15. Okay, and I set aside this alone for B. So for B, the upper 4 bits will be 0, 0, 0, 0, and the lower 4 bits will go in the range of 0, 0, 0, 0 to 1, 1, 1, 1, which will be 2 to the power of 4, which is 16. Okay, so that is basically how you can view this in terms of the maximum number and minimum number of instructions you can get, okay, based on this particular design. Okay, so the next last two. Okay, so which of the following storage architectures use implicit operands? Okay, so implicit operands means you do not have to specify it, specify which particular register you are going to use, because the instruction itself will by default use a particular register. Okay, so one of it is accumulator based architecture. So in accumulator based architecture, you have, for example, accumulator A or accumulator B, and using the instruction, okay, the particular instruction, it will automatically know which register to use. Okay, so you don't need to specifically say it in the instruction. Okay, it is implied. Okay, same for stack-based architecture. In stack-based architecture, you automatically will usually take from the top of the stack. Okay, so the data is on the top of the stack is what is used to extract the data and update and so on. Okay, so again, these are some of the older architectures, okay, of past. Okay, now we very much use register-based architecture and of course memory-based architecture as well. Okay, so this is again what I said just now. The implicit operand in stack-based architecture is store of the stack, whereas in accumulator-based architecture, it is a register called accumulator. Okay, so again, these are older processor architectures. Okay, like the past Motorola and so on. Okay, it was a accumulator-based architecture where you have accumulator A, B, C, and so on. Okay, and then you sort of imply which accumulator you're using through the instruction itself. Okay, so that actually sort of wraps up the quiz questions, okay, for this week. Okay, so we still have some time. Do you all want to try one more coding exercise? Yes, no? Okay, so let me share one more sort of coding challenge. All right, and okay, so those of you who want to drop off, we can drop off. Okay, or if other questions you can ask. If not, you can attempt this. All right, so this is very similar to just now. Okay, the only difference is instead of saying that it is 132-bit data and I'm comparing byte 0 with byte 3, I am saying that I have now 4 integer elements, and I want to compare element 0 with element 3. Okay, element 0 with element 3. That means what I'm saying is, okay, is basically it's an array. Okay, it's an array. That means what you have is you have an array of 4 elements. Okay, the first element, okay, for this example is say 0 x 0 0 0 0 0 0 1 1. This is 0 x 0 0 0 0 0 0 2 2 0 3 3 and 0 0 0 0 1 1. So in this case, okay, you have 4 elements, and what I want to do is I want to check if element 0 and element 3 are the same. So it's just a slight extension, all right, just to make sure you understand how to address elements correctly. How do you address these various elements correctly? So in terms of okay, so I'm just going to extend from here. Okay, so what I'm going to do is I'm going to put in a dot data. Okay, so dot data is to specify data elements in my code here. So I'm going to put in these 4 elements 0 0 0 0 0 0 1 1. Okay, so I'm first going to keep element 0, okay, and element 3 the same. Okay, so what I'm going to do is to make sure I'm able to point to that location, I need to load the address, okay, of my array, which is in this case the name is value, and I'm putting it into S1. Okay, so and then I set T0 to 0 as before. Okay, now when S1 is pointing here, okay, so now what is happening is register S1 is going to point to this first element here. Okay, so I want to take this, okay, I want to take this and put it into my register, any register. Correct. So for example, I can say load word into T1 and 0 S1. That means wherever S1 is pointing to, okay, I take that content and I put it into register T1. Okay, now the next thing is I need to do the same thing into another register. Okay, but what is the offset? So the offset is based on number of bytes. So from here to point to the next element is +4. Okay, element 1 will be +4. Okay, if I point to the third element will be +8. If I want to point to the last element, will be +12. Okay, so I need to point to 12 bytes away from where S1 is. Okay, so I need to have an offset of 12 from S1. So branch if not equal T1, T2 to next. Okay, so you can see it's very similar, except that now I first point to where S1 is. So I point to where this data array is in my memory, which is with the label value, and then I load the first element, which is offset 0, and then I load the last element, which is offset 12. Okay, and then I compare both these elements. Okay, so we're going to run this again on QT-SPIM. Yeah, you can use LI also instead of LA. It still works. Okay, because basically what we want is we just want to put this, I know everything. No, LI will work if you know where this is going to be stored. Okay, if you use LI, then you need to specify the address. Okay, so the address we sort of know because it is always this starting address. Okay, 1000 1000. Okay, but yeah, if you are using a label, then you need to use LA. Okay, what is this index? Okay, so let me run through this first, then I will address your questions. Okay, so if I run through this step by step, so you can see over here in this data segment, you have this 4 data type. Okay, 00011, then another 2 variables, and then 11 again. Okay, so if I run through this step by step, okay, so you can see that register 17 is pointing to the first element, so I put it into register 9. So 11 comes here, and then 11 comes here into the next register T2, and then I compare. Okay, so if they're equal, then I set it to 1. Okay, similarly, if I were to change this to maybe okay some other value, okay, so you can see that now the first element and last element are different. So when I run, will not update your register. Okay, so let me just, there's a question here on the quiz. Let me come back here. Question 3. Okay, so the question is this, what kind of program would generate code like this? Okay, because the offset or displacement would be a multiple of 4 most of the time. Okay, so the final address, okay, is the one that needs to be a multiple of 4 when you're using load word or store word. Okay, that means whatever is in this example, whatever is in register 12, when I add with negative 227, that final result should be a multiple of 4. Okay, so even if the actual offset that you see is not a multiple of 4, it can still be fine because it depends on what value is in the register. Okay, so I think that's all I have for today. If there are any other questions, you can stay back and ask. If not, I'll see you all next week.